about today is basically our universe, how we see it in very high energy gamma rays. And this is the most powerful band of the electromagnetic spectrum we can investigate something in. But first thing first, so where exactly we are? I thought it would be a nice thing to ask my terminal. So where is VERITAS? Where is the very energetic radiation imaging array? And the answer when I hit enter is the following. So VERITAS is a ground-based gamma ray instrument that operates at the Fred Lawrence Whipple Observatory in Arizona in the US. So we are exactly here, very close to the border with Mexico. And the VERITAS array consists of 4 optical reflectors for gamma ray astronomy in very high energies. We'll see that in a few slides from now. As I said, we're located near Tucson at an altitude of roughly 1,300 meters, which is equivalent to 4,000 feet. What do I have to do when I come here on site is basically take a flight from New York, land in Tucson, and then drive south the I-19 and then up to the mountain following this nice instruction. The road is pretty nice and leads straight to the observatory, straight to base camp, where I'm actually now. Okay, so this is my geographical location, right? But you can see something behind here. And so the next obvious question is, where am I? Well, it's not as big as the one that you know already, most likely from late broadcasts. So it's not as big as the one for Mars mission, but effectively, what you can see here is our mission control. So this is our control room. And this is where all the magic happens. Let's say like this. Basically, well, one would rather say this is where we can monitor all of the magic that is happening in the universe. As you can see, we have several controls, each one serving more or less one specific purpose that can go from atmospheric monitoring to the telescope drive system. And since this is a live tour, I actually want to show you my favorite control, which is the tracking software. So I'll stop my sharing for a second and go next to Control 04, where we typically have opened the tracking software. See here from left to right are the 4 telescopes of the VERITAS array. And we can monitor their azimuth and their elevation in this band. And we can control each of the telescope individually. We have a list of targets. We have a tab, which is an alert for extremely energetic and explosive events that can happen at random at any time. And we need to promptly repoint at them. So we have also an interface that does that job. And well, the first thing that maybe is jumping to your eye is that everything is red. So you see here interlock, but it's actually a good thing, meaning that this is a system that is enabled right now. So an interlock system that avoids accidental moving of the telescope when somebody is on the platform. So right now we are in the middle of the afternoon. Obviously, we're not operating the telescopes, so everything is stopped and locked. All right, so you've seen our mission control. And we have said where we are, where we actually monitor what's happening with the telescopes. And now let's come to the outline of the talk. This is more or less what I want to talk about. So there are 3 main points. So gamma rays and very high energy gamma ray astronomy. I'll walk you through what are exactly gamma rays, what are their sources, and if we look at the sky in gamma rays, more specifically in very high energy gamma rays, how does the sky look like? And how we can detect these gamma rays both from the ground and from satellite experiments. Actually, what we are interested in here at the VERITAS Observatory is ground-based experiments. I will then walk you through the so-called imaging atmospheric Cherenkov telescopes technique, which is the technique that we use to detect these gamma rays. I will show you what is the principle of operations of this telescope, and I'll go through a brief review of past, current, and next generation observatories. And finally, we'll have a live tour from the platform of telescope 3 of the VERITAS array. So let's start with gamma rays and very high energy gamma ray astronomy. What are gamma rays? In very short, they are light. And if you want to put it in a nice way, they are light on steroids. It's very, very energetic light. And before we actually look into how the sky looks like in very high energy gamma rays, I wanted to point out why, at least in my opinion, it is important to go beyond the highs, as I say in my title here. What you can see in this slide is a schematic of the. Is anybody drawing on the? Yeah, okay, maybe that was a mistake. Right, what you can see here is a schematic of the electromagnetic spectrum from radio to gamma rays. And especially important to me is the energy scale, which is outlined here. So first of all, some background terminology. You might have heard like joule is the unit for measuring energy. Well, in our field, we are dealing with scales which are much, much smaller than the joule. And for this reason, we measure our energies in electron volts. Electron volt is defined as the amount of kinetic energy that a single electron gains when it's accelerated from rest through a potential difference of 1 volt in vacuum. And also some background on the numbers. This is important. What you see on the scale right here are powers of 10. So in astrophysics, at least for the kind of astronomy that we do, this is typically what matters and what we're dealing with. So all that matters, I could say in a way, are powers of 10. So one, of course, you know, 10 to the 1 is 10, 10 to the second is 100 times, 10 to the minus 2 is 100, and so on. Visible light that you can see right here has energy of the order of few electron volts, say 1 for simplicity. The whole electromagnetic spectrum spans from billions the energy of a visible photon, and we are in the regime of radio waves, to billion times and beyond. Actually, here the scale stops at 1 million, but it goes much, much further. And the energy we usually observe with VERITAS are thousands of billion times higher than the one that we have in visible light. So also what is nice to see from this graph is the following. What we can observe naked eye represents really a very small portion of a much bigger picture. If you're a music enthusiast as I am, we can use a nice musical comparison. So if we limit ourselves to the optical band, would be like playing just 1 octave on a piano, while we actually have about 70 at our disposal. And gamma ray, the gamma ray band alone spans 20 octaves and offer the possibility to investigate the most powerful phenomena of the universe. Well, now that we have more or less in mind the energy scale we're dealing with, so extremely high energy, much, much higher than the energies we have in visible light. The next question that we want to answer is, what are the sources of gamma rays we can think of? All right, I bet that most of you are thinking something like this. So nuclear fission is the most dramatic one we can think of, as it makes us think immediately of nuclear bombs and explosions. Another one is the decay of radioactive elements, for example. And if we think about what gamma rays can do, well, what we usually think of is mostly the biological damage that gamma rays can inflict. And that more often than not is less amazing than what Dr. Bruce Banner experienced when he became the Hulk. But having said all of this, there is so much more to this picture that most of us might have in mind about gamma rays. So here I want to give you like a few examples of gamma ray sources that are basically everywhere, from our, I'll call it from our solar backyard, so from our solar system to outside our galaxy. So the first place we want to look at is our immediate backyard. I called it here our solar backyard. And what emits gamma rays in our solar backyard is our sun itself. And specifically in what are called solar flares. So solar flares are explosive blasts of light and charged particles that happen on the sun's surface, and they can produce gamma rays by several processes. The energy released in a solar flare accelerates the charged particles to very high energy. It could be, for example, very high energy protons that strike matter in the sun's atmosphere, in turn produce what are called neutral pions. These are neutral subnuclear particles that promptly decay in gamma rays. So this on the top left is an image in extreme ultraviolet radiation. And what we see here is a full sky map of the Fermi-Lat Gamma Ray Telescope. So this is a telescope that's in near Earth orbit and detects gamma rays. What you can see here, the line is our Milky Way, our galaxy, and the bright spots are gamma rays emissions. So you see a very bright spot in coincidence with the center of the galaxy. You also see a bright spot here, which is the Vela pulsar, and usually it's the brightest continuous source that the Fermi-Lat telescope detects. But on this very particular day in 2012, I believe 2013, the sun suddenly became the most the brightest source in the whole sky because of the gamma rays that it emitted in this solar flare. So the sky, the sun was 1,000 brighter than the brightest source that we usually see in gamma rays on this day. Now let's move a bit further. Let's go in our galactic backyard. So let's go in our galaxy. One of the most interesting sources of gamma rays in the galaxy are supernova remnants, which are basically the leftover of star explosions. It consists of a blast wave that accelerate particles at its shock fronts, and these particles, these accelerated particles, can interact with matter or radiation fields, producing, as a consequence, gamma rays. Another source of gamma rays, but this time outside our galaxy, are the so-called active galactic nuclei, which consists basically of supermassive black holes at the center of a galaxy that accretes material from the galaxy's central region, which is very dense, and emits narrow beams of particles that get accelerated, and through mechanism that we will see in the next slide, can emit in turn gamma rays. The takeaway message here is, what do all these sources have in common? Well, they are explosive and very energetic. their gamma ray emission can help us trace particles that are accelerated at these sites at very, very high energies, near the speed of light. So now that we have reviewed the sources of gamma rays, we can start by reviewing the processes that can generate gamma rays. The classification that I like to propose here is by type of interaction. So the first type of interaction is accelerated particles and matter. So the red ball here is a proton. It's most of our cosmic ray composition. So if you go outside and look for a cosmic ray, 99% it's a proton. And then the other particle that we are always interested in is electrons and positron, the electrons antiparticle. So a proton can be accelerated by one of the sources that I mentioned above, interacts with the matter in the interstellar medium, produces a subnuclear particle that in turn promptly decays into gamma rays. And this process is called pi-zero decay. Another process that involves accelerated particles and matter is when an electron interacts with the electric field of another charged particle, which can be an electron itself or another nucleus. This is called Bremsstrahlung process, namely braking radiation. So the electron arrives into this cloud, decelerates under the presence of the electric field of another electron or another particle, and emits a gamma ray. The second type of process is the interaction between accelerated particles and radiation field, typically infrared light from stars or cosmic microwave background. So what happens here is called inverse Compton scattering. You have an accelerated electron that hits on a lousy photon, so a low energy photon. It kicks it, and this photon gets boosted up to gamma ray energies, while the the incoming electrons goes out and goes its way. The last kind of process that we can look at is accelerated particles within a magnetic field. And this kind of emission is called synchrotron emission. So you have a charged particle, typically we're interested in electrons, it spirals within the influence of magnetic fields, and in this spiraling emits gamma rays. So why is it important to know what kind of processes can produce gamma rays? Well, what we can do with this is actually fingerprinting the particle population which is responsible for the gamma ray emission. And I found this nice strip online, and this is kind of exemplifying the process we go through when we try to identify which kind of particles originated the gamma ray emission. It's very difficult for us. Most of the time, it's very difficult to tell whether it was an electron or a proton and which kind of process caused that gamma ray emission. To kind of trace the particles that produce the gamma rays, we use this plot on the bottom part of the slide. It's a bit complicated, but bear with me. So this plot is called, these plots actually, one on the left and one on the right, are called spectral energy distribution plots. So it basically is a plot of the energy versus the energy per the number of photons per energy beam that we have, spanning from radio band to very high energy gamma rays. So let us start from the data points. What we see in blue, green, violet, and black are the points that we actually collect with several experiments in different wavebands. So blue, radio, green, X-rays, and violet and black are gamma rays. After we collect data, we can make some assumption on the particle population that could have produced such an emission, right? throughout the spectrum. So our model has to account both from the emission here and for the emission here. And as we've seen in the previous slide, different particles in different conditions can produce gamma rays in different ways. Most of the time, at least for the energy ranges we are interested in, we want to find out whether the emission was from electrons, so-called leptonic, this is only a fancy word to say electrons and positrons, or hadronic emission, so mainly protons. In very high energy, high energy to very high energy, we have a characteristic signature of proton acceleration, which is, can you see the mouse here, which is called the pion bump. And so in one case, we model our emission as if it were coming mostly from electron, and you can see it doesn't really fit here. So these points are left out of our overall model, which is the sum of the different processes, and this is this overall black line. But if you look on the right, if we hypothesize that we're looking at protons, we actually obtain a better fit of our experimental data. So the takeaway message here is that we can, though most of the time it's very difficult because it can be a stainless steel, as it said here, we can actually fingerprint the particles that have generated the gamma ray emission. Finally, we want to see how our galaxy, how our sky actually looks like in gamma rays. But first, we all know how our galaxy, our sky looks like in the optical band. So basically between 400 and 600 nanometers, which correspond, as we said before, to very, very low energies, few electron volts. So it looks more or less like this. You see some bright sources, the brightest being the center. You see dark gas clouds. But what happens if we look at very high energy gamma rays? How does the sky look like? Well, it looks like something like this. So it's what I'm showing here is slices from the inner part of the Milky Way. So this is the big picture. Now I'm zooming in into this region, and I'm looking into this inner part of our galaxy in very high energy gamma rays. So you see it's a lot of background noise, and this is all the red spots that you see. But also you can identify different kind of sources. We have point-like sources, barely visible here. We have extended sources, which are big blob-centered field. Or we have shell-like sources. So we have a brighter rim emission and a shallower emission in the center. Basically, other than having different spectra, which was what we showed in the slide before, we also have different morphological features that can help us identify which kind of source we are looking at. Now, well, it's nice. We know there are gamma rays coming from the sun, our galaxy, and outside our galaxy. But the question obviously becomes, how can we do to detect them? And before we go into that, before we go into the technique that we exploit here at the VERITAS side, this figure is of paramount importance when we approach the subject of detection. I mean. And this picture represents the transparency of the atmosphere for radiation of different wavelengths. In the domain of gamma rays, so the blue part is not transparent. So every radiation incoming here gets absorbed by the atmosphere. So this is the domain of gamma rays. And the atmosphere of our own planet is basically opaque to radiation at these energies. So you can do basically two things. The first one being you go above the atmosphere, you go into space, and this is what satellite experiments do. Maybe the most famous one is the Fermi-Lat Gamma Ray Telescope. And these kind of telescopes cover like high energy gamma rays, but the lower hand of the gamma ray emission from our sky. Now, if we want to go at higher energies, so at billions, trillions of times the energy of visible light, we can do two things. Either we wait a long time because the fluxes decrease dramatically with energy. So either we wait a long time, or we build a huge instrument. Obviously, it's not that easy to fly a huge instrument to space, so we have to find some way to observe gamma rays from the ground. But I actually just said that gamma rays are absorbed by the atmosphere. So how do we do the trick? And this is what I'm going to discuss in the next slide. The main idea of the imaging atmospheric Cherenkov technique is to exploit the atmosphere itself as a calorimeter. And what is a calorimeter basically? It's an instrument where an incoming photon, so incoming radiation, can progressively degrade its energy through a series of interactions. What happens in our atmosphere is the following. This on the left side of the slide is a schematic of what happens when a gamma ray impinges on the atmosphere. So a gamma ray photon with energy, let's say E naught, so initial energy, doesn't really matter, enters the atmosphere and splits, generates an electron and a positron. In turn, this electron and positron, through Bremsstrahlung, which is one of the processes we outlined before, emit new gamma rays. These gamma rays, in turn, emit new pairs of electrons and positrons, and so on, generating what it is called an electromagnetic shower. All right, but this is not the end of it. So we'll see the telescopes that we have here are actually optical telescopes. So they reflect light in the visible band and near ultraviolet band. So we can still not detect the secondary gamma rays produced in the shower, nor the charged particles. But yeah, then what do we actually see? What we see is a byproduct of this electromagnetic shower. The electrons and positrons that are generated in this shower can go faster than the speed of light in the atmosphere. We are in a medium, we are not in vacuum, so we are not violating any principle here. It's simply that in a medium, the speed of light is reduced by a factor, which is the refractive index of the medium where the light propagates. So here, this n is for our atmosphere very, very close to 1, but it's slightly higher. So particles can actually travel faster than speed of light in the atmosphere. When they do so, secondary light is emitted, basically very beamed along their path, which is called Cherenkov light. This electromagnetic shower, the electrons and positrons emit Cherenkov light and generate on the ground what is called a Cherenkov light pool. And if you put a telescope in this light pool, you can actually image the original shower by means of an instrument, a camera, basically. In some way, it's very similar to the camera that we have in our phones, but a bit more sophisticated. And we are able, with this instrument placed in the focal plane, to reconstruct energy and direction of the incoming gamma ray. So how do we do so? As I said, we place a telescope, we are within the light pool, and we look at the shower. So the light is collected by a large dish, which is here, and focused in the focal plane instrument. And that what we see in this focal plane instrument looks something like this. So the image of a gamma-induced shower looks like an ellipsoid in the camera. And we know how to parameterize this ellipsoid, and through this kind of parameterization, which is called Hillas parameterization, we can reconstruct several parameters of the shower. So energy, mainly energy and direction. Well, can we do better? And the answer is yes. So in this slide, we are in the situation in which we are basically seeing with one eye only. But what we can do better is doing a stereoscopic reconstruction. So adding more telescopes to the array. And this is what is done in basically all of the currently operating Cherenkov telescopes in the world. And having stereoscopic reconstruction of the shower leads to improved angular and energy resolution. So we can determine the energy and the direction much better than when having only a single telescope at our disposal. Well, so far, I've only told you about gamma rays, but gamma rays isn't the only thing that we have outside there. Like the top of our atmosphere is constantly bombarded not only by gamma rays, but by charged particles, by cosmic rays. And also these cosmic rays can produce a similar shower. The problem is, how can we distinguish such shower in the camera? It will essentially produce something very similar to this, but not so much. And here what we would see in the case of a gamma ray shower on the left side, and in the case of a proton-induced shower on the right side. So you see the gamma ray shower in the image is mostly a regular ellipse, and the proton shower in the field of view of the telescope looks like an irregular blob. So by defining parameters that describe the ellipse, we can see if this blob has parameters that are outside the range of interest, and we can say with more or less high confidence, yeah, all right, this is not a gamma ray. We discard it in our data analysis. It has nothing to do with the gamma ray source we are looking at. Right. So this was the Cherenkov technique. This technique has now a very long history, has developed, well, very long, but not so long compared to other kind of telescopes, like, for example, optical telescopes or radio telescope. It's a relatively young field, and it has experienced a huge development in the last 20 to 30 years. The first, like the predecessor, the pioneer of this kind of technique was the Whipple 10-meter gamma ray telescope at the Fred Lawrence Whipple Observatory. So this was basically the first imaging atmospheric Cherenkov telescope that was successfully operating and detected very high energy gamma ray sources in the sky. And was actually very recently decommissioned, I believe in 2013. All of the telescopes that actually operate right now are, in a sense, descendants of the Whipple the Whipple 10-meter telescopes. So you can see already some of the features that we will see also in the live tour. The reflector is composed of several facets. In the case of Whipple, it was roughly 250 hexagonal facets that provided like a total reflective area, pretty big, but smaller than the ones that we have now, roughly 80 square meters. And so the light incoming here would be reflected onto the focal plane instrument, which is this one, which contains the detector instruments, which are called Photomultipliers tubes, and I'll show you in a second. Well, the evolution from Whipple are the current generation IACTs. So at present, there exist three main IACTs that perform indirect detection of very energy gamma rays on the ground. And all of them consist of stereoscopic systems. As I said before, it's much more advantageous of having more than one telescope when observing a gamma ray source in the sky. The one on the top left of this slide is the MAGIC telescope array. The one, and it's located in the Canary island of La Palma in Spain. we have already seen VERITAS on the bottom of this slide, and we will go to telescope 3 in a bit. And on the top right part of the slide, there is the HESS telescope array, which is in the southern hemisphere. Currently, is the only telescope array of that operates that is below the equator. And actually, on my record, I only missed the Canary Islands, but I've been to both telescope arrays, VERITAS and HESS, and I can tell you that both of them are amazing instruments. Yeah, as I mentioned, I was mentioning just a few instances ago, we're gonna go here for our light tour. So this is how the current generation looks like. What can we do better? Well, typically make it bigger and make it, in our case, more diverse. So this is an artistic rendering of how the next generation that we are currently building of ground-based camera telescopes is going to look like. It's going to look like a huge array of different telescopes with different sizes, large-size telescopes, medium-sized telescopes, and small-sized telescopes that address different energies in the gamma ray spectrum. One thing that you can notice in this artistic representation of the next generation, the Cherenkov telescope array, is that most of the telescopes here have a classic, so-called Davis cotton design. So it's a single mirror design with a camera in the center, but then you can maybe spot some intruder, let's call them this way, with a different geometry. So we have, I'll show you this better in the next slide. We have two mirrors and the camera right in front of the secondary mirror. This kind of telescope is called the Schwarzschild-Couder Telescope, and this is the prototype I'm actually working at in this month that I spent at the FLWO in Arizona. How is the pSCT different? Contrary to the classic design where we only have one mirror, the pSCT has two. And here is the primary mirror, M1. Here you cannot see because we are looking at the back, and these are the baffles of the secondary mirror. And here, roughly here where I'm pointing with my pointer, there is the instrument, focal plane instrument, there is the camera. So Cherenkov light is collected by the primary, reflected onto the secondary, and finally it's projected onto the focal plane instrument. And why we want to do that in the first place? It's because most of the existing, actually all of the existing telescopes have several optical aberrations that we can correct with this new design. One interesting thing to note is that this design has been thought of since the 30s of the last century, but the mirror technology has developed such as it was only possible to realize these kind of telescopes, I mean, very, very recently. And the prototype Schwarzschild-Couder telescope is the only medium-sized telescope featuring this design. It's the first telescope so big to have been built with a dual mirror technology. And how does the focal plane structure of the telescope looks like? So it's a modular structure. This is what we do. I mean, we cannot build a whole camera, a whole thing. It's a pixelized instrument, as also the camera in your phone. And it has kind of a hierarchical design. So the full camera is comprised of 9 sectors. There are these cross sectors here, which are hosting 25 modules, sub-modules each, and the corner sectors, which have a bit less. And the full camera will be composed of more than 11,000 pixels. Just to give you an order of magnitude, an MSC now will have of the order of thousands. So a single mirror MSC has a like 1,000 detectors. And this dual mirror detector, since it allows us to focus the light on a much smaller and compact surface, will have a much finer pixelization with a much higher image resolution of 11,000 pixels. This is something really unprecedented for this technique. Right now at the prototype, we have equipped only the central sector, which has obviously a reduced field of view of roughly 2.7 degrees, but the whole thing will have a very large field of view of 8 degrees. And if you compare it with the field of view of the VERITAS telescopes that we will see right now, it's almost twice as much. So the VERITAS telescopes have a field of view of roughly 3.5 degrees. This thing here, when fully populated, will have a field of view of 8 degrees. So why do we do this system in the first place? It's complicated, it's expensive, but there are several reasons. We have superior optical angular resolution over a very wide field of view. And as I was mentioning before, the largest IACT field of view is currently less than 5 degrees, and the VERITAS telescopes themselves have 3.5 degrees in field of view. Also, we have big eyes, as I'm mentioning in the title of the slide, but we also have a sharper view. By focusing the light on a smaller surface, we can use much more finely pixelized camera, for which we use state-of-the-art sensors, which are called silicon photomultipliers, which I've actually worked on for a big chunk of my scientific life. And also we can have improved electronics. All these things can lead to better sensitivity and reduce observation time. Just to give you an idea, I put these pictures here. So I told you before about the difference between a gamma ray shower and a proton-induced shower. So these two images are for a gamma ray shower. And you see here, this is a classical telescope. And this is the image how it should look like in a Schwarzschild-Couder telescope, the one that we are building right now at this observatory. You can see the greater detail. Actually, this is, I mean, really breathtaking for people who have been used in the field. Me pretty recently, like the last 5 or 6 years, but people in the field which have been used to look at this kind of images, looking at something like this, it's what we could call a wow factor. Just a quick note on the detectors. So what we will be using, what we are actually using in the prototype Schwarzschild-Couder telescope are called silicon photomultipliers. So first of all, can you all see the instrument that I'm holding right here? Amy or Mike?
Yes.
All right, this is the instrument that we use in the VERITAS telescopes. This is called photomultiplier tube. So light impinges here, it converts into an electron that then gets accelerated by a dynode structure in here where a very high electric field is applied. And just to give you an idea, we bias these instruments at 1,000 volts. And you see, they're compact, but not that much. They're kind of bulky and very fragile. These new instruments that we are using here, the so-called silicon photomultipliers, are rugged, definitely more sensitive. They have a higher efficiency in the detection of light, and they can be made in much smaller sizes. So the pitch of this one, which is actually not even one of the most recent ones, it's pretty old, but it's just to give you an idea, it's 4 millimeter squares. And this is a bit more than 1 inch. So it's pretty impressive. What a silicon photomultiplier is in very, very brief, it's a solid state sensor, and it's composed of thousands and thousands of microcells, which can be as small as less than 10 microns, actually. And each of these microcells effectively behaves as a digital detector for incoming light. So let's say a photon is impinging on the microcell. if it gets absorbed, it generates a light pulse, a current pulse at the detector ends. And if you put more cells together, you can detect more photons. And so you will have a light output which is proportional to the number of photons that have impinged on the silicon photomultipliers. Well, this is all nice. We have seen the simulation of how a gamma ray looks like in an SCT, how a proton looks like in an SCT. Well, right, nice. What a nice resolution, but these are only simulations. So the question is this instrument working? The answer is yes. So very recently, a bit more, a bit less actually than 1 year ago, we have announced the detection of our first gamma ray source, the Crab Nebula, which is kind of the reference source for very high energy gamma ray astronomy. What you can see here on the top right of the slide is an animation of the gamma rays detected by the pSCT. And what I show here are also excerpts from the press releases that were published when we announced the detection. I put here one in English from the Smithsonian and one in Italian from INFN, which is one of the institutes we collaborate with, just to outline what I'm going to show in the next slide, which is all of this, all of what we do daily in our careers, in our research experience. It's a strong collaborative effort from all over the world, basically. And the slide that I would like to show here is giving you a sense of all the effort that is poured into the realization of a prototype telescope. These are all the institutes that participate in the prototype SCT and will participate in the upgrade of this instrument we're building. Yeah, right, we have detected the crab. We have built these nice new instruments, but basically we never stop. And this is what I'm doing right now, right here at the FLWO. And as you can see in the caption of the picture, you can spot an Italian postdoc, which is very, very careful, opening the back of the camera of the pSCT for technical inspections. And this was taken a couple of days ago, actually. What does this mean? This means that despite the success, we're obviously looking forward to improve our software and data acquisition for the prototype SCT, our optical alignment, mainly of axis. And we are right now working on the upgrade of the focal plane instrument. So I've told you before, we only equip the central sector of the camera, while we have a much bigger area at our disposal. And the upgrade will populate the full camera with the full amount of pixels that it can host, and we will move from 600 pixels to more than 11,000. And this will bring the telescope field of view. This will almost triple the field of view of the telescope. We will upgrade the photosensors. So we will be using photosensors from Fondazione Bruno Kessler, which is a publicly funded research institute in Trento, Italy. I was working there for a couple of years. And this is one of the leading centers in the field of photosensing with these devices in the world. We'll also have upgraded preamplifiers, and we'll have upgraded electronics. All of this, of course, as for many fields, this was unfortunately true, has been stopped or like paused for a bit due to the pandemic, but we didn't stay there like crying over our shoulders. We implemented a remote observing system, and we're still able to take data with a local observer or more than one. If more than one, we're obviously seeing separate rooms. So we have what I call here a locally remote observer which is actually in the cubicle in the other room. And we have a remote observer. And this is a picture of a remote observing setup in New York. So some concluding remarks on very high energy gamma ray astronomy. I hope I convinced you that very high energy gamma ray astronomy is a very powerful tool to explore the energetic universe. And in the last 20, 30 years, the technology has improved so much, and it has opened the window to the highest energy possibles in the gamma ray band. We are currently involved in the construction of the next generation observatory, the Cherenkov telescope array. And within the Cherenkov telescope array, we are building a high potential, first of its kind, again, Cherenkov telescope. We have validated its technology by the detection of the Crab Nebula, and we're going towards the upgrade with lower noise electronics, more efficient detectors, and preamplifiers. So this is what we're gonna here. This is what we're gonna see now. So we are right here. Actually, I'm in here in the VERITAS control room, in the VERITAS building, and these are the 4 telescopes of the VERITAS array in order T1, T2, not in order T4, and then T3, and we're going about here. And some facts here on the telescopes. They have an optical reflector which is built of a very large number of segmented mirrors, 350, a finely pixelated camera. With these devices, it's composed of roughly 500 pixels. I already commented on field of view, and the energy range that we can look at is TV energy range, basically very high energies in gamma rays. And how does this whole thing works? So this is the optical reflector, and you have a photon that reflects on the mirror surface into the focal plane instrument. And what you see here, so these circles here are the instrument that I showed before. It's the photomultiplier tube, and these are light collectors. Light impinges here, gets collected, and then gets piped into these photomultiplier tube detectors, which produce eventually a readable pulse that then gets fed into the electronics. And this is how we can record the photons from an electromagnetic shower. And I think now I'm ready to go outside, and I'll ask you to bear with me for 3-4 minutes, just the time to go there.
During this 3 or 4 minutes, Professor Reshmi Mukherjee has volunteered to say a few words. She's the head of the Barnard astrophysics group.
As Massimo is walking from the VERITAS control room to the telescope site, I just wanted to show you this picture here, because he was right here inside the control room. So you should be able to see my screen here. These are the 4 VERITAS telescopes. This is actually a very old picture. And if you can see my mouse, let's see, I'm going to try to use my pointer here.
We can see your mouse.
Okay, great. So he just walked out of this room, of the control room. Here are the cars parked. So as you can see, this is the base camp of the Fred Lawrence Whipple Observatory. And in fact, the 4 VERITAS telescopes are located in the parking lot, which is actually an odd place for telescopes to be, but there's a bit of a story with that. But if you were to come in, and if the site were open, unfortunately, we are actually closed now to visitors. But in normal times, anybody going to Arizona, this is part of the Smithsonian Astrophysical Observatory, and it's in the Coronado National Forest. So if you're interested in doing a little hike around that area, just feel free to drive to the telescope sites, and you'll actually come. You don't see the gates here, but right here where my arrow is pointing, you'll be driving in here, turning right, and right here is the visitor parking lot. And you can just pull up your car and get out and just walk around the telescopes. And these yellow posts sort of protect the telescopes from, you basically not allow anyone to cross that line. But it's very accessible. And between 9 and 5, you can just request a tour of the telescopes. What you see here right in front is telescope 1. Massimo is going to go behind this visitor and office building, which you see here with the green shed, onto telescope 3, T3. And in fact, that's the one that you can see as you drive south from Tucson towards the telescopes. And you can actually see the Santa Rita Mountains, and you can see Tucson in the background. It's a beautiful site for observing, very remote. And we kind of miss not being able to go to the site for actual observing. But because of COVID, we are doing a largely remote observing. And we're very fortunate that the Smithsonian Astrophysical Observatory, the field and technical support group was able to set that up for us. That we haven't, we can go back to observing and not lose observing time with these 4 telescopes. But I think that it's really remarkable how quickly we were able to switch into remote observing and not lose dark time with these telescopes.
So you run at night because of the photodetectors, and I take it this site, there's very little, there aren't cities nearby or anything that would produce light.
Yes, that's right. So we do run at night, and that was actually a question that came in. Is because although we are gamma ray detectors, we are actually looking at optical light, and that's this blue Cherenkov light, which is the shock wave that's emitted in the atmosphere. It's faint flashes of blue light. They just last they're gone in few nanoseconds. I think they last about a few nanoseconds in time. But that's right. So we do have to pick a site that's dark, where the weather is dry. We can't be observing when it's cloudy or if there's any humidity, that doesn't work. So really the choice of the site is very important for us. And in fact, for most, as you know, most astronomical telescopes, you really have to make a good choice in site selection. But you can see here that it's really remote. It's very dark. There's not much. Tucson, in fact, Arizona is very sensitive to night light pollution because there are several astronomical telescopes there. And we do, when you're observing, the protocol is you don't move the telescopes until after twilight. So the sun has to be down before you move the telescopes. We can only observe in dark time. So we know we have something called a shift schedule based on the moon calendar, which we fill up. It's well thought out and well planned because as you can imagine, these telescopes, as Massimo was saying, at least these VERITAS telescopes are about 3-degree field of view, 3.5. So you can only observe a small part of the sky. And making the observing plan, that's really, it's well informed and well thought out and much debated in order to, select the portion of the sky that you want to observe. But Mike is right, and what you see here are these photomultiplier tubes that Massimo was showing, he had in his hand. You can see these little shiny things. It's almost, you can't really zoom in, and I wouldn't be able to show it to you, but we have these things called, sort of cones that you protect. You want the light to filter in and focus. They're almost like these coffee cups that sort of zoom into these cones, and that's what you see here. Shiny, you see these tubes taking something like 500 billion samples per second, then we analyze post, after taking the data.
So what you can see here, it's what I described in my talk. I hope you see me waving in the optical reflector. This is, as I was mentioning, a segmented reflector. So this allows us to exploit all the back supporting structure that maybe you can actually intuitively see right where there is that missing mirror. We have several monitor systems you might see some of the cameras that are mounted. So for example, the one in the center of my field of view at the moment is the one we use to monitor the focal plane instrument of the telescope, which is right behind my shoulder. And let me point you to it in the reflection in the optical structure. So the lights arrives there, and it goes back to the focal plane instrument, which is currently closed, obviously, because we are in broad daylight, and it's composed of roughly 500 pixels. Each of one is one of those bulky instruments that I showed you in the first part, in the last part of the talk. So I hope you can see this better. So just to convince you that I'm in the focal plane, can you hear the echo in my voice? That's pretty amazing. And this what happens also actually with visible light. So it gets reflected there, comes into the focal plane, and this is how we detect in the end the secondary radiation from a gamma ray that impinges on the atmosphere. Right below my feet, there is the electronics and a whole bunch of other control systems that we use to operate these telescopes, other than the remote control systems that we have in the VERITAS control room. What else can I show you? Oh, something nice, which actually doesn't work that well. I'm kidding, I'll show you why. We also have a nice owl there, which is supposed to scare the birds away, but they actually like the telescope as much as I like it, at least. And so they come here at the most improbable time and cause a bit of damage to mirrors, but not that much. And well, this is what the telescope is. And you can see, so let me move a bit around. You can see here where I'm pointing with my finger, one of the other telescopes of the array. And behind this building, if we could actually move without losing Wi-Fi connection, I could show you the prototype telescope. And well, I'd like to conclude by showing you the scenery that we get from here that is pretty breathtaking, as at least as the observations per se are. So let me share with you the view of the mountains and of the desert that we have right here from the platform of T3. And yeah, I'd like to conclude by thanking. I have really a lot of people to thank, but especially in this occasion, Barnard College, obviously, that allowed me to be here in this difficult time. The SAO staff that is constantly supporting, and the NSF, which is funding my research, and also friends and family that joined at such a late time from the other side of the ocean, and obviously all of you for joining me in this journey, exploring gamma rays and the energetic part of our universe.